Thank you. Thanks for the introduction and the invitation. So when I was preparing this talk last week, there were a lot of students, so I tried to keep the technical details to a minimum low, but somehow all the technical details got covered in the talks, and also the students, I think they've gone back to attending classes. But anyway, it's been a long week, too, for some of us, so I'll stick to my original plan. So as the board dries, let me start with some motivation, which is also going to be a background for these kind of objects. So let me start with an elliptic curve over the rational, say, of conductor NE. Conductor of E over Q, let's call this NE. So I can look at the modular curve of level NE, and the underlying Riemann surface can be described as the gamma naught NE orbit of the compactified upper half plane. And this elliptic curve is modular, so there is a modular parameterization, which is a non-constant map phi E from this Riemann surface between these two Riemann surfaces. Right? So now let me fix an imaginary quadratic field K. Imaginary quadratic. And let me choose any element tau in this imaginary quadratic field, which has imaginary part greater than 0. So I can look at the class of tau here. It's not a and then the image of this class under this parameterization is a priori a complex point on the elliptic curve. But then by complex multiplication, this is in fact going to be a rational point on this elliptic curve. So I'll just write this complex multiplication. So phi E, let me call this point as p tau. So phi E of tau is a rational point on this elliptic curve. So it's defined over the maximal abelian extension of K. So this is somehow exploiting theory of complex multiplication. It's in some sense rough class field theory, in some sense, yeah. So the natural question one can ask is, how further can we go beyond this situation? So we start with an imaginary quadratic field. Complex multiplication helps us produce rational points on elliptic curves. And just a remark, so before I say anything further, p taus are called CM points. And they're quite crucial in the work of Gross-Zagier and Kolyvagin. In proving BSD when the analytic rank is 0 or 1. So I'll squeeze in a when here. Yeah. So producing rational points on elliptic curves, they have their own interest. It also came up in Sujatha's talk 2 days ago. So yes, so at the beginning of the century, 2001, H Darmon tried to investigate if we can produce some kind of analog when working with real quadratic field. So just to change notation, I'll call K prime to be a real quadratic field now. And his construction, he could produce what are now called as Stark-Heegner points. So I'll still say, let's say P prime tau just to be keep it distinct. So these are actually points. So he could produce, I'll say this is, I don't know, this is not quite the theorem, but let's say this is Darmon. So these are local points. So P is now some prime that exactly divides the conductor of this elliptic curve, and then K prime P, the P-adic completion of K prime. Sorry. And the construction, it's very local. It's a nice framework, and it sort of seems like there should be an analog. So H Darmon, he also makes conjectures that these points should be global points on the elliptic curve. And there's a precise Galois action, Shimura reciprocity, and so on. And then since then, so these are called, so p tau primes, I call them SH points in short for Stark-Heegner points. So there have been some other construction of similar kind, so I'll just note them down here. So the first generalization was due to Samit Dasgupta. This is in, I think, 2004. He wrote down Stark-Heegner points on modular Jacobians. So Henri's construction is for elliptic curves, and then you can pull it back to the Jacobian of the modular curve. And then subsequently, Mac Trifkovich, this is, I think, 2006 Duke paper. This is again Stark-Heegner points on elliptic curves, but now they are defined over imaginary quadratic fields. And then Matt Greenberg, soon after, I believe this was 2009 or thereabouts. So it's the real quadratic analog, or totally real analog. So Stark-Heegner points on elliptic curves defined over totally real fields. And then more recently, I think around 2012, is due to Victor Roger and Marco Seveso. They realized that these constructions carry over to higher weight, so they looked at elliptic modular cusp forms of even weight. So their construction is looking at this space, these even weight forms, and they produce Stark-Heegner cycles. The word cycles is a bit ambiguous, and I'll explain why we call it, or they call it cycles, and why we also continue with it. Yeah. So this is sort of, there are some other constructions due to Matteo Longo and Mark must do as well, but so far so good. And then our construction is almost done. It'll be in the archive in a couple of weeks. We've extended this construction for Bianchi modular forms. So let me fix some notation. So F will be an imaginary quadratic field. Some of the notation will overlap with this introduction. So let's say class number 1. So there are about 9 choices. This is just for ease of notation. And let me fix the rational prime P unramified in F. Rational prime ramified in F. And then associated to P, I'll fix 2 embeddings. So I infinity will be an embedding of Q bar into C, and then IP will be an embedding into QP bar. So if P splits as, this is just P, and then script P prime in F, then script P will be my prime above IP. Above P under, above P under IP. That'll be somehow sort of the important prime lying above P for us. All right. And then I'll fix some levels. So N will be an ideal in OF, in the ring of integers of F, such that N is of the form Pm, where P and M are coprime. So this is fixing levels. Then I'll fix a Bianchi cusp form F, say of parallel weight K plus 2 and level N, such that it's also new at P. So P is in the level, and I want F to be new at P. I'll fix Yeah, I can fix this right away. L will be a finite extension of QP. Be sort of the base field, so it will contain the image of Hecke eigenvalues of F under IP and many other things. But anyway, so far it's just a finite extension. Now my role of this K prime here. So K prime was degree 2 extension over Q. So I'm going to fix K over F to be a quadratic extension of F. So it's all relative, say, of discriminant dk, such that it satisfies two. There's a hypothesis on K prime on K. So it's that P should be inert in K. And then all primes, all other primes in this level, so all the primes that divide M will be split. And so this hypothesis, it's called Stark-Heegner hypothesis. It's kind of tailor-made in the sense that my base change L function, so F is a form on defined over F. I can look at its base change to K. This vanishes at the central critical value. Maybe this one's better. Yeah. Yeah, so I can look at this base change L function. Yesterday there was a talk on epsilon factor in a similar setting. So this condition, if you work it out, the epsilon factor will be -1, which means that the L value vanishes. In fact, I can go a bit further. So let me fix OC to be an OF order in K, say of conductor C that's relatively prime to both the level and the discriminant. And I can look at the ring class field associated to OC, so I'll call it HC. So this is, look at the Hilbert ring class field, I'll call this GC. It's also isomorphic to Picard group, this order. So I can look at the base change of F to HC. So this admits a factorization. So this will be base change over K and then twisted by character chi. Yes. So I can make sense of the order of vanishing at the central value. K by 2 plus 1. I'll squeeze this here. And then each of these L functions have the same sign as F over K, so there's a lot of vanishing. So in particular, this order is quite big. It's at least the order of this group GC. So by I was about to say Birch-Swinnerton conjecture, which is not sort of very wrong in the setting, but yeah, this is by Bloch-Kato conjecture. By Bloch-Kato, you know that some Selmer group, it's been coming up in talks for the last 2 or 3 days. I'll write ST because there's some condition, I'll get to this later. So the Selmer group, so these Bianchi forms, they admit a Galois representation. We've seen this the last week, even sometime this week. There is a Selmer group associated to this Galois representation. This has positive dimension, so I'll call this as dimension over L. So the Galois representation will take values in L. So that's the kind of extension that I'm fixing. So this has dimension at least equal to the order of this class field. Right, so this is the setting. We know some L function vanishes. We should be able to produce elements in a Selmer group. So the goal is to try and get there, but it sort of stopped quite short of it. Anyway, so our Stark-Heegner cycles will be sort of elements in a local piece of this. I think I've been pressing the chalk too hard. Is that much better? Okay. I'll go ninja style now. So all these constructions that I talked about, I mean, they're all quite different because they're looking at different objects. But they can be broken down to, I like to think of it as a three-step process. So it's been said quite well enough that to understand the arithmetic aspects of automorphic forms, they come from studying its cohomology. There was a course last week, a couple of talks this week as well in the discussion meeting. And so the first step is to construct a cohomology class. So this will be very similar to Fabrizio Andreatta's talk earlier this week. So this will come from over-convergent Bianchi modular symbols. Right, so let delta naught, sorry, I'm dropping in more notation here. So this will be the set of degree zero devices on the cusps of F. So in particular, I can look at this space. I'll call this VKKR. R is some F algebra. So this will be VK of R, tensor, VK of R. VK of R is polynomials in R. Of degree less than or equal to K. So I'm taking two copies of it, and then I have a PGL2F action on this space. VKK. So this will be, let's say gamma is some element here. I can define this action as follows. So this will be gamma P, tensor. On the second component, acts by complex conjugation on F. Oh. I won't describe this action, but everybody knows what this will look like. Yeah, so I can form this set. So this will be Hom from delta naught to VKK dual. Let's look at coefficients in C. So C is an F algebra, obviously. You can make sense of this action. This has an action of this level, this congruence group gamma naught n. So I can look at the elements, the fixed elements here. This will be the space of classical modular symbols. Or all these classical Bianchi modular symbols. And to the form F, I can associate an element here. So the Heck eigenvalues match with F because there's an action of Heck operators on space. And just as in Fabrizio Andreatta's talk, I can p-adically deform this space. So, okay, I'll drop this arrow for now. So I can define over-convergent Bianchi modular symbols. So let me look at this space. I'll call this P1. Actually, let me just call this P1P. So this will be projective line on FP. If P is inert, P equals P. And it's slightly different when P splits. So it's P1FP. Tensor VK of P bar. P splits, yeah. I told you, script P will be the prime that concerns us, but when it splits, you sort of have to throw in a factor. So this is slightly different from Andreatta's talk in the sense that the space is slightly larger than his coefficient field that he was looking at. I mean, okay, I'll make this precise now. let me call AK of P1P L to be a set of L-valued locally analytic functions on P1P. But this space, I mean, so in Andreatta's talk, there was no point at infinity, but somehow this comes in. So I'll say that it can have a pole at infinity. So except for a pole at infinity of order at most k. So that's the notation that comes in as k. And you can sort of look at the space, mainly precisely because my form f was new at p. So you can sort of patch this up to infinity. And then I can define this space of over-convergent modular symbols. So this will be, look at its L dual. So this will be distributions on P1P. Again, say L-valued. And then Hom devices. But then enlarging this space means that we'll have to modify the level as well. So I'll tell what gamma is now. But then this will be my space of over-convergent modular symbols. I mean, again, with Andreatta's talk, there's a slight difference. I've thrown in this module cusps, so then groups come on to H0 instead of H1, but, you know. What's that?
Same thing with FQ replacing C. FQ1 of FQ.
What's that? What's that? Oh, just projective line or FP. Yeah, F complete. Oh, FP is F completed at P. So P is a prime, so this is P-adic completion. Okay. This one. O. So this is OFP. Okay. So VK is just this. I'm looking at polynomials of degree less than or equal to K on OP. Yeah. Okay. So I'm sorry. No. It's okay. Okay. Actually, yeah. Let's just look at P1 of FP. Here it will be. Yeah. Okay. So this will be AK of P1P. Okay. I can write this more clearly as FP, comma L tensor VK of P bar. Yeah. So if P splits, I look at locally analytic. Yeah. Sorry. Yeah, I wrote this down in the last minute and it didn't. Yeah. I'm sorry. Yeah. So I should call this as. Okay. Yeah. Okay. More clear now. Anyway, so we have these over-convergent Bianchi modular symbols. So here gamma will be some Ihari subgroup. So this will be gamma naught M amalgamated over gamma naught N. I can write this as MP as well. Or if you don't know what this means, just think of it as gamma naught M, and then I'll allow denominators at P. So this is some kind of Ihara group. Anyway, I'll write this more clearly, the export there. All right, so I have the space of over-convergent modular symbols. Hom delta naught, dk P1P. And then there's a projection, there's a surjective map, the space of classical modular symbols. So this will be gamma naught N now. Delta naught, VK, K, So yeah, I can look at these coefficients in L. So there's theorem of Hida that says that these Bianchi modular symbols take values in a number field. So I'll assume that number field can be embedded into L via IP. So there is this map, and there are analogs of the theorem that Fabrizio and Riata spoke about even in the Bianchi case. So this form is nu at P, which means it has small slope. So I can look at the F isotypic component on both these spaces. And this surjection says that on the F isotypic component, it's an isomorphism. Because this form is classical, it has small slope. So this big space, when you just look at the F isotypic component, it will be one-dimensional. Okay. So this is, let me call this, I don't want to keep writing this again, so I'll call it modular symbols at gamma, L-valued, isotypic component. So this is one-dimensional L vector space. And this, I had a modular symbol here, called this mu f. I can lift this uniquely to an overconvergent symbol in this place, say psi f. So the space will be spanned by psi f for me. Right, okay. So this was the cohomology class that we want. And then there's a homology class that I'll write down. And the idea is to somehow integrate this cohomology class along this homology path that I write down. Most of this appeared in some sort of, in Mahesh Kakde's talk as well. So some sort of his construction also goes through here. So I'll just erase this here. This is section 3, homology class. Right, okay, so let me call by HP unramified. This will be some kind of Drinfels unramified upper half plane. So this is P1 QP unramified, and then I throw away the points at FP. This is set complement. Is it fine? I mean, kind of ambidextrous with this. Is it complement or quotient? It looks fine? Okay, this is the set complement. So this is unramified. Drinfels upper half. You can also look at Drinfels upper half plane as such. There's no reason to restrict to this. But anyway, P is unramified, so it's fine. Then, yeah, okay, I'll also fix this by some Galois group. Keep it unramified by L0, so L0 will be my maximal unramified extension, sub-extension of L. It's just because we want to set, I mean, maybe it won't come up in the talk, but we have some kind of Shimura reciprocity, so for that you need to work with a smaller space. All right, so then in principle, I can look at the divisors on this Drinfels upper half plane, tensor this over Z with module we had from before, VKKL, yeah, of L, and then also on. So my Ihara group gamma acts on this module. So for being Mobius transformation here, and then the usual weight K action here. So I can look at the set of gamma co-invariants of this module. Right. And associated to our OC was a OF order in K. I can look at optimal embedding psi from OC into M2. So This is, yeah, last time I gave this talk, someone thought this was modular forms of A2. So this is 2 by 2 matrices on OF 1 by P. So I'm looking at ring of integers, but I'm also allowing denominators by P. So you see, OC is an order in K, so the units has a free rank 1. So I can fix a generator for OC star, and then looking at psi, I'll get a matrix, and from the matrix, I can write down elements here. So the elements we write down, this gamma coinvariance module will depend on psi. Or rather on OC is fixed, so it really depends on psi. If you move along psi, from the set of optimal embeddings, you'll get different elements here. So far so good. We've written down a cohomology class IF and homology class d psi. That's not good notation now. Let's call this phi f now. Sorry, I don't want to, both these objects will go into the integration, so this is going to be confusing. All right. Now comes the part, this is called, we call it P-adic integration. So we can write down double integrals. So this will be, first we can integrate along the usual cusps. So degree 0 divisors on the cusps, and then again, degree 0 divisors on Drinfels upper half plane, on VKK. So this will again be right. So we have two maps like this. So this will be, let me call them phi f odd P and phi f log P. So if you recall from Mahesh Kakde's talk, he also had these p-adic or valuation and p-adic log maps. So these are very similar. They come in the same way, and then phi f odd is related to L values, phi f log is related to derivative of a p-adical function, and the sort of phi f log is an L invariant times phi f odd. Those are the two maps, and then I'm going to play around a bit. So I'll write phi f to be minus phi f log direct sum phi f odd. So this will be a map from degree 0 divisors on the cusp, degree 0 divisors on p-adic unramified plane times VKK, and I'll write this as a map in this form. So I can look at the dual of the modular symbols attached to F. And I'm taking direct sum there, so this will be a direct sum here. And in fact, this map will factor through the gamma coinvariance. So essentially, phi f will be a map like this. So this is the shape that it takes. Notice that the homology class that I wrote down is slightly in a different module. So let me just, for brevity, I'll write df. So recall this was the F isotopic component of the Bianchi modular symbols, and then df is just direct sum of this. So a priori, this is a two-dimensional L vector space, but one of the first things that we show is that this has some p-adic austerity property. So this is a filtered phi n module over L. You all know what it is. Denis Benois gave a wonderful course last week of dimension 2. Right. I'll continue this theorem. So let me just take an interlude and then set up some stuff here. So our Bianchi form was a parallel weight 2, nu at P. So P exactly divides the conductor now. And then there is a Galois representation, P-adic Galois representation attached to this. So this is rho is from GF to GL to L. So I can restrict this to a decomposition group. I'll say, let's call this rho P. This is from gal FP bar over FP, GL to L. So the automorphic representation attached to F, it's Steinberg at P. So there are standard conjectures in, I guess, local global compatibility that rho P is semi-stable. Actually, yeah, you know this notation now. So rep L GFP. What was, semi-stable on top or? Okay, yeah. So, I mean, some people have announced results of this sort, but nothing has appeared concrete. But anyway, I think this will come out soon. So this is something we can assume, and we will. So in particular, I can attach the Fontaine-Mazur-Diordnay module. So this is the semi-stable of rho P. So this is also a filtered phi n module over L, rank 2. This is over FP tensor L. Then I can sort of look at its, how do I say, restriction to L, or yeah, I can restrict this representation to L. So I'll look at this as DFM of rho P restricted to GL. And so this is part one. Part two is that under a weak trivial zero conjecture, DF is isomorphic to DFM of rho P restricted to GL. So the weak trivial zero conjecture, this says that, so this is a filtered phi n module, it has an L invariant. L invariant will be the type of Darmon cohomological L invariant. So the trivial zero conjecture is an equality of L invariance, and equality of L invariance sort of lifts to an equality of phi n modules. Okay. So we've also assumed that this representation is semi-stable, which means that by Bloch-Kato's, we have a Bloch-Kato exponential map. So this is from rho P restricted to GL modulo fill K by 2 plus 1, the same object, the Bloch-Kato exponential. So this is an isomorphism to the local piece of the Selmer group. Tate dual twist. Yeah. And by this theorem, this isomorphism can be, actually I call this DF. So this is DF modulo fill, the filtration on DF, so I can look at its fill K by 2 plus 1 piece. And by this theorem, this is also an isomorphism. Right? And then I can plug back this P-adic integrals back into this picture here. So DF, yeah, let me just not write this. So DF is exactly the space where it's valued. So there is a map. So I'll call this phi F. So this was H0 gamma coinvariance, delta naught tensor. Ramified tensor EKK L. So this was my map phi F. Phi F was from a map here to DF, but then I can project this. And it's another result that we show that when we project, we can remove the degree 0 divisor condition on the unramified plane. So this is the module where the map factors through. This is phi f, this is the isomorphism we prove, and then this is Bloch-Kato. So essentially, I have a map from this module of gamma coinvariance to a local Selmer group. And then if you recall, we wrote down elements d psi here. Let me call this map log aj, and I'll tell you why. So in particular, log aj of d psi is some si in a local Selmer group. So AJ stands for Abel-Jacobi. So in normal terms, you would have a Chow group, kind of an algebraic variety, and then you'll have an Abel-Jacobi map, which will land in some kind of a local Selmer group. But of course, in the Bianchi setting, we don't have any motive, so we can't really make sense of those objects. Nevertheless, we can construct such maps which sort of mimic it. That's also one other reason why we call elements like d psi as cycles. It's an ambiguous word, but they sort of seem to behave like they would as algebraic cycles. But anyway, so the upshot is that we produce classes in a local Selmer group. Because somehow the main result is really in these two steps that we show, and that sort of leads us to construction of local Selmer classes. And similar to H Darmon's 2001 paper conjecture, we also formulate a similar conjecture, which is that formulate Darmon style conjecture. So my field K, so P was inert here. HC is some ring class field over K, so P splits completely. Right? So I have an embedding, I think I'll call this log P, just to be consistent with Denis Benois talk. So I have an embedding of this form. Which means that this will induce, and L, we assume that it contains Kp, so this will induce a map at the level of Selmer groups. So this is a semi-stable Selmer group at Hc with coefficients in Vp of f. Again, you have to do a twist. And we have elements here, Si. The conjecture we formulate is that there exist global classes, say fancy Si, in this global Selmer group, such that under this localization map, we precisely get these classes that come out from this P-adic integration theory. Right, okay. And in fact, yeah, just a remark, the phi odd that I wrote down, we know it's non-zero. It's related to L values, and there's some results that say that it's a non-zero map. Phi log could be 0 if the L invariant is 0, but the L invariant is expected to be non-zero. So eventually, our local classes are non-zero classes here. So that's one remark I wanted to make. Anyway, these conjectures, they seem quite hard. Even Henri's original conjecture has been proven in very few number of cases, but then there's some work going on. I guess there's some connection to... you found some connection to... Deshalit? You found some connection of Henri's conjectures to the Drinfeld Tower or something? Not really? There was some talk about it. Anyway. Yeah, okay. So, yeah, Henri-style conjectures, they're quite unknown yet. Some cases have been proved. So, anyway, I'll finish with this and then we can have a longer coffee break before the last talk of this conference. So, there's some work in progress, but very early stages. Is to prove, I didn't give this a name somehow. Let's call this conjecture 1 or conjecture A. Is to prove conjecture A. I think we have some ideas. Anyway, I won't say much about it. When there are two scenarios, so my form F, this is a Bianchi modular form, is in fact the base change of an elliptic modular form. It's BC of, say, capital F. F is now an elliptic cusp form of level. Yeah, so I'm going to start with, I think when we start with the elliptic modular form and then base change to Bianchi, and also restrict to the case that K is biquadratic in CM. In particular case of the form F prime. So F is imaginary quadratic, K was degree 2. Now I also wanted F prime to be imaginary quadratic. So once I restrict to this case, I think we can sort of show global classes. So the idea is that you have Heegner cycles coming in from both these fields. The idea is to do some kind of 3-variable P-adic function and then P-adic Gross-Zagier type formula, and then show that the global classes coming from the Heegner cycles would actually restrict to global classes expected from Stark-Heegner cycles. Anyway, we've just started working on it. So I don't want to say anything more about it, but I think we can do this. So yeah, I'll stop here.